Thank you. Can everyone hear me all right? Yes. All right. Okay, so I'm going to talk to you about a little bit of machine learning today and how I'm trying to make that pertain to exploit kits. At the outset, I want to be sure I clarify that I'm not really an expert in exploit kits. I mean, it's not like terribly complicated stuff going on there, but I think it's important to say that. And as much as I'm not an expert on exploit kits, I'm less so of one on machine learning. It's just sort of something I've played around with for the last 3 or 4 months. So, of course, this seemed like a really good idea 3 or 4 months ago, but now you get to see what I, in fact, know about this stuff. Something I like to do when I give a talk is I like to give people a few options so they can sort of choose their own adventure. This is, I think, good for the second one. And then I've got 20 minutes to get into some like pretty complicated topics. I mean, 20 minutes, 45 minutes, there's never enough time when you start talking about things like this. So this talk's geared to be high level and hopefully give you some ideas, but definitely not to be a record of scientific fact. These are mostly my own musings from the work I've done the last few months. As Mark said, I'm a systems engineer at FireEye. I've been there for about 2.5 years now. Before that, I worked on the GE CERT out in Michigan. Go Blue. Before that, I worked as a host forensics consultant for an undisclosed vendor out of Boston. And if anyone else has been a consultant before, then you might feel like I do, where the best skill I feel like I learned as a consultant was that in the time it takes to get a call to go somewhere where you have to show up on site and be an expert, and teaching yourself on the plane what you need to know to sound like an expert, it's a really useful skill. And something that helps, because it's nice to not sound like a moron. Okay, I work for Chris Sanders, who already spoke today and spoke yesterday. He wrote Applied Network Security Monitoring. And also I'd like to give a shout out quickly to the Rural Tech Fund, which he also founded, which does a lot of great work. You can check it out at, I think it's ruraltechfund.org. Is that right, Chris? Okay, yeah, so check that out. And then I like to throw in fun facts when I can. A fun fact here is you'll see Jason Smith is a co-author on this book. I wouldn't go so far as to say Jason's my friend, but one time he did abandon me in a dark parking lot on the side of I-95 in Connecticut. As far as I know, that was an accident. Okay, show of hands, does anyone remember me speaking last year about the digital Thetford wall? Okay, a few people. Yeah, I remember a couple of you. So I just wanted to quickly provide an update to that story because I've seen a few people around here that have been asking me about it because they were really curious to know about the exciting conclusion. So anyways, I'm just going to go through a couple slides real quickly. And this has nothing to do with anything, but some people were interested, so I'm going to share it quickly. What we see here is my house is the blue one in the distance, and there's a big 50 by 30 foot wall lurking in the foreground there, very sinisterly. That was, my neighbor put that up last year because he didn't like looking at my house. So someone, this really got out of control. I was like on national news and stuff with this story last year. Anyways, what I'd like to say here is you should never kick a man when he is down, and that is not something that Chris Sanders believes. Yeah, thanks, Chris. This hurt a lot. And okay, so anyways, I gave this talk last year all about the Thetford Wall and what happened to me there. And if you go on Google, you can find all sorts of crazy stuff about it. But about 30 days after talking here last year, the situation resolved itself when the state of Vermont told my neighbor, who's also almost the governor of Vermont at one point, that she needed to remove the wall or they were going to do it for her. So the tweet up there was the last I saw of the Thetford Wall. And that's all I've got to say about that. Okay, so now our story today really begins back when I was a lad in high school, I guess. And what happened was, at the time, this was in the early 90s, I really wanted to be, I guess it was called like a hotspot doctor back then. I wanted to sort of be someone that was like dropped into remote areas to respond to things like Ebola. I've just always had a passion for infectious disease. So I went to college and I majored in biochemistry. Well, I started doing that. I ended up switching to computer science after a while, but I'm actually still about a semester short of a biochem degree. As part of like a biochem education, one of the things you learn a lot about is evolution. Now, I personally think that evolution is kind of taught poorly in a lot of schools in our country for a lot of different reasons. So if you're not familiar with it, just wanted to go through a couple things here because it sort of relates to what I'm talking about. I think a good way to think about evolution is, in some ways, to see some examples that aren't right. So before Charles Darwin, there was a guy, Jean-Baptiste Lamarck, and his sort of famous example of how evolution worked is he believed in this idea of use and disuse. So essentially, he thought like the way giraffes sort of evolved were that they had to continually reach for the food on higher levels of trees and things, and it was just through the act of like one generation of things sort of needing to stretch and whatever, the next generation of that organism would incorporate that, and everything would just sort of would adapt in that way. Not really based on anything other than use and disuse. The similar thing would be like, he believed that like if he cut off his toe and then his kid cut off his toe and then his kid's kid cut off his toe, eventually you get a person that didn't have a toe there. And that's not how evolution works. But at the beginning of the 1800s, this was sort of groundbreaking because he was trying to think about, well, how do things change? Now, Darwinian evolution is predicated on natural selection. And this is a really famous example that you'll see a lot. It sort of explains the idea simply and elegantly. And what you have here is, this is the peppered moth, which this natural selection occurred in the Industrial Revolution in England. So late 1800s. But what happened is the peppered moth sort of started as it was on the left, where it was white and black speckled. And that was fine before the Industrial Revolution because it would land on trees and that camouflage would protect it. What happened during the Industrial Revolution is that the trees, there was so much pollution, the trees were covered with soot and ash, so that the peppered moth would actually stand out, and they would get picked off by predators much more easily. So what happened with variation in the gene pool is that natural selection sort of allowed the progression of the peppered moth to become more solidly black because it allowed it to evade detection by its predators when it was on these sort of ashy trees. So that's like a very clear example of how evolution sort of works, one that's simple to understand. But the big thing with evolution is that it's very incremental, right? So it's not something that happens overnight. It takes several iterations or generations to be able to accumulate these different changes that occur. And finally, I like to show this just because I think it's so cool. But moths are neat because they can adapt really quickly to a new environment based on genetic variation and the relatively short lifespan. So this is the emperor moth. And I'll ask you real quickly, can anyone tell what its adaptation is that makes it successful here? Yeah. Yeah, right, exactly. It makes a face. And I actually have a better example of that on the next page. So what you see here, this is the same moth. But what's cool is that it's actually evolved to look like the face of an owl, because an owl is a predator of the birds that prey on the moth. So it scares its predators away. And it's even to the point where you can see it's the spots on the wings that look like eyes. They're not perfectly round because evolution isn't about perfection. It's about being good enough so that you can survive to reproduce another day. Which there's like, that's a kind of interesting idea. But what's neat to me about this, what I just think is amazing, is you can even see how that's not actually reflected light in the spots on the wings. That's actually how it's evolved to look like reflected lights on eyeballs, which I just think is amazing. So I love science. So all this idea of evolution and stuff, I think about this a lot. It's sort of like the lens I view the world through now. And what happened a few months ago is there's a guy in my team, his name is Dustin, and I was sad for him because he was like on the 20-something iteration of a rule he was writing for the Angler exploit kit. And if you know anything about exploit kits, the popular ones, they'll change frequently. And it's hard when you're writing rules to detect this stuff to sort of keep up with it. What I have here also are just some other exploit kits that were sort of popular in the last year or two. So this is what really gave me the idea of, I was thinking, you know, if these exploit kits are changing so rapidly as the sort of malware authors are trying to evade detection, I wondered if over time that is something that could be predicted, sort of like evolution. Is it evolving in a way that I could guess how it would change before it changed? And that was sort of the idea behind what I was doing here with my research. I'd like to give a shout out to Brad Duncan from malwaretrafficanalysis.net here, because that's where I get all of my well, mostly all my samples from. It's a great resource for people in our field. If you're not using this site, you should be. But it's just invaluable for studying exploit kits. So definitely check this out. And I assume that most people here are familiar with exploit kits, but high level, a victim visits a website whose server's been compromised by cyber criminals. Victim is typically redirected through various intermediary servers. The victim lands at a rogue server hosting the exploit kit. Exploit kit gathers information on the victim and determines the proper exploit to deliver based on the software the victim is running on their machine. An exploit is then delivered based on that information. And if it's successful, then a malicious payload gets downloaded and executed. That's the 20,000-foot view of exploit kits. So I wanted to sort of take the idea of this in evolution, and I thought, well, this sounds sort of a lot like what I'm hearing about machine learning these days, which is sort of the new buzzword, the hot thing. So again, sort of high level, but some ideas and how machine learning works. It's a branch of AI. But it's a very, I would say, probabilistic-based approach. So I also think of it as very analytics-ish, although I've not heard everyone refer to it that way. But machine learning, it relies on examples and experience. So with what I'm familiar with, there are three sort of different kinds of machine learning, and it's people might have some other subcategories or whatever, but this is sort of my understanding. All right, so there's reinforcement, unsupervised, and supervised learning. To give you an idea of how reinforcement works, think of chess. Reinforcement is actually a subset of supervised learning. So when you think of chess, and you think about a computer game that is playing someone, if at the end of that game, if the computer loses, then it can take that and say, okay, that's a bad outcome, and learn from that. That's sort of the idea of reinforcement. If it wins, then it did some right things. It can also use that as a way to sort of feed the algorithm, feed itself. Thank you. So unsupervised is really, you get the thing that stands out to me with unsupervised is the idea of clustering. And that's essentially, you have some data, and if you just, I really should have put up a slide for this, but I didn't. But data might clump somewhere on a graph in different regions, right? You might have like think of something simple like file size, or something usually numeric that's easy to plot. But if you see clusters of things, today's algorithms with machine learning are really good at recognizing that and deciding, okay, that should belong in a special category from this other clump of things. And that's sort of the basis of unsupervised learning. The sort of thing I was doing with my example was what's called supervised learning. And with supervised learning, the way it works is you essentially already know the answer. So what you have to do is you train the data that you are looking to be able to detect. So in my case, if I've got a bunch of exploit kits or PCAPs from exploit kits, I can run that through Bro. I can generate some data. I know that with this particular data set, that these are malicious, so I can use these to train my model. And I can also then take benign data and sort of do the same thing to teach it, okay, this is stuff that is not malicious. So what you do with supervised learning, it's really the high-level, simple three-step process. You collect training data, you have to train a classifier, and then you make predictions. And that's really it. So like I said, I use Bro to get HTTP proxy data. And essentially what you're doing is you're kind of creating a simple function. You feed data into it, and you get a label out. And in my case, my label out was going to be this is malicious or this is benign. Okay, so an example for training my data, this was done with the magnitude exploit kit. And something you can say, this is, as I'm training it, I've got HTTP method, user agent, refer, cookie varies, URI length, URI string, and label. So I've got 2 malicious samples there and 2 benign. And with today's algorithms that are available, that really does all this stuff under the covers, and you don't even have to be an expert in this stuff to do. You can feed this into these different frameworks like scikit-learning, and sort of over time, with lots of samples, train your program to be able to detect what malicious or what benign looks like. So there's a couple of issues here that I'll talk about quickly. One of the things is when you're doing like machine learning, you really want to keep everything in terms of numbers, because that's how sort of math happens, right? So if you have like a string like get or post, you need to somehow convert that to a numerical value. And there's different ways of doing that. Like you could say if you want to get, okay, if it equals get, that's a 1. If it's something other than a get, then it's a 0. It could be that simple. In the case of magnitude, a lot of times with the payload, you're looking for a 32 character string. So if you can actually look for the length of the string, that can be a good numerical, okay, 32, that's a number I can use. 32 is going to be good. Anything other than 32, it's not going to be malicious. And I'll talk about the problems with URI strings in just a second. Okay, so once we sort of collect and start to train this data, we need to be able to sort of have our program execute this decision tree. And while this looks pretty complicated, this is like literally a line or 2 of Python code. That's really pretty basic. So I'm just taking those classifiers that I showed you from before, those labels, the data that we feed in, and we just take it one step at a time. So if I give it a new sample, this is a new log, a new HTTP proxy log that comes in. Well, first I check, is it a get? If it's not a get, then I know that it's benign for this magnitude EK thing that I'm looking at, right? But if it is indeed a get, then it just goes on and it cascades on down until, if it meets all the conditions, then we can say with a reasonable amount of certainty that it is in fact malicious. And that's just an example of how a decision tree works in machine learning. And that's really what your goal is. You're trying to get your data into a way that you can sort of give it, yes or no questions that's very binary, 1 or 0 sort of things. Real quickly, I just like bag of words. I think it's fun to say. But we have this issue with machine learning where it doesn't work really well with strings. So you just have to figure out a way to get those strings to think of them in terms of numerical. So like I just used an example of a user agent. You could do something like, okay, if I know that this is a bad user agent, this one is not, this is normal. But if it was, I could say, okay, I'm going to assign a numerical 1 or a 0 for every like token in the string. There might be things that are sort of contraindicators, like if it's Apple or something that you don't want in there, you know that that's legit, then you might just assign that as 0 in the training data. And then quickly, Anaconda and Python. Anaconda is like pip if you've used it. It's a package manager for Python for scientific and math packages. So you can do simple commands like conda install a package. And the packages are things like numpy, scipy, scikit-learn, which is what I used for my work, matplotlib, and pandas. So all really good stuff. And then finally, my results. What I have here, it just shows the samples up at the top that I tested, and then what I found for my success rate on the bottom. So for the rig, EK, is at like a 34% success rate, Angler 0.22 or 22%. Angler can go to hell and die. Neutrino was better, I think because of the good samples I had for that. And magnitude was sort of a unique thing. It was kind of easier to detect. And I think that's why I had some better success there. So those were sort of the results that I had. There are problems with that, and I'll talk about. I just have a minute or two left here. So this isn't anything like scientific that I pulled out of this. This is my own thing that I want to share as sort of like a learning thing that I experienced here. And I think with this kind of machine learning, at least as it applies to exploit kits and things that are constantly changing, what happens is you have this problem of exponential decay. And what that means is if we have a like false positive rate on the left, 100%, and on the x-axis, we have, think of it as effort that you put into the problem. Well, with very little effort, 10% effort, we can get the false positive rate down quite a bit. But what happens is you have to put a lot of effort in to continually get that false positive rate down. And that's a problem when you're trying to do, I think, detection at scale for a lot of people, because 1% of a big number is still a big number. So like when I'm showing rates of 30%, 40%, 50% success, it's a step in the right direction, but I still think it's kind of terrible. Okay, so I think one of my issues might have been my sample size is likely problematic, just pretty small. I already made this point. Again, if you don't have a lot to look at in your board, which I don't know a lot of security practitioners that don't have anything going on, then maybe 60% rates are good for you, but I don't think it would work for me. Again, this is my own thought. I think that machine learning is probably better for variations of incrementally dissimilar patterns. The problem that I saw a lot with exploit kits is that from one version to another, there can actually be a significant change in the URI or something that I'm trying to key on, and that makes it really hard to detect. I saw some white papers out there, I think University of Toronto and Chicago, where they claim to have 99% success in detecting EKs. Bullshit. But what I think this had to do with, as much of anything, was they were looking at specific examples where they had the source code to the malware, and I think they were looking at different stages of the exploit kits. For instance, I was very interested in looking at the final stage where we had malicious payload being delivered because I spent too much time in the console. And I know that it's really important to narrow in on that latter stage for the guys in the console, because if you start investigating everything at the front end of an exploit kit, possible, exploit being delivered or whatever, it's, you'll spend all day chasing this stuff down. Like I said, exponential decay might be a deal breaker because you're putting a lot of effort in to kind of tweak things down to probably where it needs to be. And going back to the evolution idea, evolution's very incremental, often large variance between exploit kit samples, which I think is part of the reasons why it didn't work as well as I would have hoped. So, had to buzz through that at the end, but does anyone have any questions? Excellent.
All right. If there are any questions, Patrick, do you have a question that you can pose to the audience for a valuable prize? And today we're going to be going Person who answers the question is going to get a rubber ducky. No, actually, I have two questions. Yeah, we'll get a rubber ducky, and we'll have an iOS application book. So, do you have two questions?
Sure. Okay, there were three kinds of machine learning that I talked about. Give me one of the three. In the orange right here. Okay. You said you want one more?
Yeah, one more.
Okay. Let's see. This is a good one. It's a sports ball, but I don't care. Who's the greatest quarterback in the NFL? Thank you. Okay.
All right. Thank you.